So far, all the linear algebra we've done has been over the real numbers. So every scalar we've encountered belongs somewhere on the real number line. If we want to get a complete picture of the theory, however, we need to discuss complex numbers. So these are scalars that we'll end up using that aren't necessarily real. So what is a complex number technically? By definition, a complex number is some expression of the following form. Z equals A plus B times I. Okay, so what are the ingredients here? A here in this expression is what's called the real part of this complex number, and this can be any real number. The number I that pops out in this formula is what's called the imaginary unit. So this is a special number that's defined by a counterintuitive property. And this is the property that the square of this number is equal to -1. So I is just a number, and all we know about I is that its square is -1. Right away, we know that I is not a real number because the square of any real number is non-negative. What about B here? B is what's called the imaginary part of this complex number, and that can be any number on the real line. Note that we use this special notation to refer to the real and imaginary parts of a complex number. This number A here is often referred to as fancy R of the complex number. That means R stands for real here. And this number B, which is the imaginary part, is written as fancy I of the complex number. Again, I here stands for imaginary. And remember, we use fancy R to refer to all real numbers. To refer to complex numbers, we use fancy C. And so C here stands for all complex numbers. So we have a few examples here. Or we have one example here, I guess. Here, what we're saying is that the number 6 minus 11 times I belongs to the complex numbers. So this is a complex number. The real part of 6 minus 11i is equal to 6. That's the part that's not attached to I. And the imaginary part of 6 minus 11 times I is -11. That's the number that's attached to the number I. So it's important to think about how these things are structured. So we now have sort of two types of scalars. We have scalars that are real numbers, and now we have scalars that aren't necessarily real numbers. So think about the relationships here. Every real number can be considered a complex number. These are the complex numbers whose imaginary part is just equal to 0. So these are the numbers that we've been working with: 17, 0, -11, pi, e, 9/22, so on and so forth. But now what we're doing is we're sort of enlarging R to include more numbers. So every real number is also a complex number, but not every complex number is a real number. These are the numbers that have imaginary part not equal to 0. So 4 minus 3i is a complex number that is not real. 7i is a complex number that's not real. And 19 plus 2i is a complex number that's not real. So every real number is a complex number, but not every complex number is a real number. So what about the algebra or an arithmetic of complex numbers? Well, we can take two complex numbers, so z1 equals a1 plus b1 times I, and z2 equals a2 plus b2 times I, and we can, for example, add them together. The rules for addition are straightforward. We simply, to add z1 and z2, we add their real parts together, and that's the real part of the sum of the two numbers. Then we add the imaginary parts together, and that's the imaginary part of the sum of these two numbers. Multiplication is a bit more tricky. To figure out the rule for multiplication, we have to actually multiply these two numbers together and then use the property that I squared equals -1. When we go through that exercise, we find that z1 multiplied by z2 is a complex number whose real part is a1 a2 minus b1 b2, and whose complex part, or whose imaginary part, is a1 b2 plus a2 b1. We also have a special operation called conjugation. So conjugation is denoted with a line above the number. So z bar, which if z is a plus bi, that would be a plus bi bar. And this operation is extraordinarily simple, but it turns out to be super useful. To conjugate a complex number, all we do is take the same number, except we negate the imaginary part. So the conjugate of a plus b times I is a minus b times I. This allows us to define the absolute value of a complex number. To find the absolute value of a complex number, we take the square root of that number multiplied by its conjugate, which turns out to be the square root of the sum of the squares of the real and imaginary parts of the number. So we're going to end up using conjugation a lot, so it's worth understanding how it works. So there are three important properties that we're stating here for conjugation. Conjugation is additive, which means if we add two complex numbers together and then conjugate, that is always the same thing as individually conjugating the two complex numbers and then adding them together. Conjugation is also multiplicative. What this means is that if we multiply two complex numbers together and then conjugate, that is the same thing, and I have this written incorrectly here, I need to fix it, but this is the same thing as multiplying the conjugates together. So the conjugation of the product is the product of the conjugation. And finally, conjugation is an involution. What this means is that if we conjugate a number twice, we get back the original number. We also have the notion of the reciprocal of a complex number. So if a number z equals a plus bi is not equal to 0, it is possible to divide by that number. And there's a formula for 1 over z. This is given by the conjugate of z divided by the absolute value squared. And if we run through what this actually turns out to be defined as, this ends up being a complex number whose real part is the real part of the number divided by a squared plus b squared, and whose imaginary part is negative the imaginary part of the original number divided by a squared plus b squared. We can also use conjugation to test whether or not a number is a real number. To conjugate, we negate the imaginary part. But if the imaginary part is 0, that's the same thing as saying that the number is real, and conjugation doesn't do anything. So we can test whether or not a number z is a real number by checking if its conjugate is equal to itself.